The topic to be discussed in this video are distortionless line and condition for distortionless line. Distortion, distortion less, distortionless line and condition for distortionless line. Distortion less line. Generally, a signal normally consists of a band of frequencies. The purpose of transmission line is to transport a band of frequencies. During the transmission of a signal on a transmission line, it gets attenuated through attenuation constant alpha, which is a function of frequency. Generally, a signal normally consists of a band of frequencies. Band of frequencies. The purpose of this transmission line, the purpose of the transmission line is to transport a band of frequencies. A band of frequencies. During the transmission of the signal on a transmission line, it gets attenuated through attenuation constant alpha, which is a function of frequency. Another important point. During the transmission of a signal on a transmission line, it gets attenuated. Through attenuation constant. Through attenuation constant alpha, which is a function of frequency. Which is a function of frequency. Is a function of frequency. Therefore, the attenuation constant alpha is a function of frequency. The attenuation constant alpha is a function of frequency. All the frequencies will not have equal attenuation constant. That is, different frequency components undergo different attenuations. Hence, the received end waveform will not identical with the input waveform at the sending end. Next one, all the frequencies. A signal is a band of frequencies. All the frequencies will not have equal attenuation constants. Equal attenuation constants. Equal attenuation constants. That is different frequency components. Different frequency components. Different frequency undergo different attenuations. Different attenuations. Hence, the received end waveform will not be identical with the, hence, due to that attenuation of that signal. Therefore, hence the received end waveform will not be identical with the input waveform. With the input waveform at the sending end. At the sending end. This results in distortion, which is known as frequency distortion. This results in distortion. This results in distortion, which is known as frequency distortion. Frequency distortion. That means a signal is a band of frequencies. All the frequencies are imported at the transmission lines. All the signal frequencies do not have the same attenuation constant. Different attenuation constants are there. Therefore, at the receiving end, waveform will not be identical with the input waveform at the sending end. This results in distortion, which is known as frequency distortion. In order to reduce frequency distortion occurring in the line, the attenuation constant should be made independent of frequency, and the phase constant should be made frequency dependent. First one is in order to reduce frequency distortion. Frequency distortion occurring in the line. The attenuation constant should be made independent of frequency. Should be made independent of frequency. As in previous case, a signal is nothing but a band of frequencies. The purpose of transmission line is to transport such band of frequencies. The attenuation constant alpha is a function of frequency. When a signal having many frequency components is transmitted along the line, all the frequencies will not have equal attenuation constant. That is, the different frequency components undergoes different attenuations. Hence, the received end waveform will not be identical with the input waveform at the sending end. The resultant distortion is known as frequency distortion. Our aim is to reduce the frequency distortion occurring in the transmission line. The attenuation constant should be made independent of frequency. Equalizers which minimize the frequency distortions. Equalizers are also used to minimize the frequency distortion. Equalizers are used to minimize the frequency distortion. Next one, some phase or delay distortion is also there. Phase. Next distortion is the phase or delay distortion. Again, when a signal having many frequency components is transmitted along the line, all the frequencies will not have same time of transmission, but some frequencies are delayed more than the others. Different time intervals are used. Different frequency components will have different velocity of propagation. This result in distortion known as phase or delay distortion. All the frequency components will not have same time of transmission. In case of frequency distortion, all the frequency components will not have same attenuation constant. When a signal having many frequency components is transmitted along the line. All the frequencies will not have same time of transmission. Same time of transmission. Some frequencies being delayed more than the other. Some frequencies being delayed more than the other. That means different frequency components will have different velocity of propagation. Different frequency components will have different velocity of propagation. This result in distortion is known as phase or delay distortion. This result in distortion known as phase or delay distortion Two types of distortions are there on the transmission line: frequency distortion, phase or delay distortion. In order to reduce the delay distortion occurring in a transmission line, the phase constant should be made frequency dependent. In order to reduce delay distortion occurring in a transmission line, the phase constant should be made frequency dependent. As frequency changes, the phase constant of the signal is also changes. The velocity of propagation should be made frequency independent, like phase constant. The attenuation constant should be made independent of frequency, like the velocity of propagation. The velocity of propagation should be made frequency independent. Next, derivation. Conditions for distortionless line. Consider propagation constant of the waveform, that is gamma is equal to, gamma is nothing but propagation constant. Gamma is equal to alpha plus j beta, that is equal to square root of r plus j omega n g plus j omega c. In order to avoid the distortionless transmission line, r is common term here, 1 plus j omega L by R. Here G is common term, G into 1 plus j omega C by G. That is equal to square root of Rg 1 plus j omega L by R and 1 plus j omega C by G. If omega L by R is equal to omega C by G, if omega L by R is equal to omega C by G, omega is cancelled, therefore L by R is equal to C by G, or R by L is equal to G by C. Both are equal. Therefore, propagation constant gamma is equal to square root of Rg 1 plus j omega L by R omega L by R is equal to omega C by G is equal to omega L by R. That means 1 plus J omega L by R. Therefore, gamma is equal to square root of Rg 1 plus J omega L by R whole square. That is equal to root Rg 1 plus J omega L by R. J omega L by R. That is equal to root Rg plus root Rg J omega L by R. Here gamma. We know that gamma is equal to alpha plus J beta root Rg plus root Rg J omega L by R. Alpha is equal to root Rg. Compare J coefficients. Therefore, beta is equal to omega L by R into root Rg. This is equal to omega L. Here R is root R into root R. Root R is cancelled. That is equal to root G by R. Root G by R. This is the alpha is attenuation constant. Attenuation constant. Attenuation constant. Beta is phase constant. Phase constant. In order to avoid a frequency distortion on the transmission line, the attenuation constant should be made is independent of frequency. The attenuation constant alpha is made is independent of frequency. There is no frequency term involved here. Totally based on root R and J elements only. If this condition is satisfied, R by L is equal to G by C. Next, in order to avoid the phase or delay distortion, the phase constant of the waveform made frequency dependent. That is, the beta is directly proposed is equal to omega L by R and root Rg. Here omega is equal to 2 pi f. Therefore, beta is dependent on frequency of the waveform. Another way of derive this one is here gamma is equal to root Rg 1 plus J omega L by R 1 plus J omega C by R here. C omega by here G not R G. Omega L by R is equal to omega C by G. Omega C by G is omega L by R. Gamma is equal to square root of R plus J omega L G plus J omega C. R is the common term here. R into 1 plus J omega L by R G into 1 plus J omega C by G. Omega L by R is equal to if omega C by G. Therefore, gamma is equal to root Rg. Omega L by R is equal to omega C by G. 1 plus J omega C by G. 1 plus J omega C by G. Therefore, gamma is equal to root Rg 1 plus J omega 1 plus J omega C by G. 1 plus J omega C by G. This one is root Rg. Gamma is equal to alpha plus j beta. Alpha is root Rg. Beta is equal to root Rg omega c by g. That is equal to omega c into root r by g. Root r by g. This is another way of derive this alpha and beta. In this case also alpha is independent of frequency, beta is dependent. Beta varies linearly with the frequency. Next one. Here gamma is equal to square root of r plus j omega l g plus j omega c. G plus j omega c. In previous case, r is the common term. Here we common terms are l and c. Therefore, l into r plus r by l j omega. Here c into g by c j omega. That is equal to root lc r by l plus j omega g by c plus j omega. But for a distortionless line, already derived, r by l is equal to g by c. R by l is equal to g by c. For distortionless line, r by l is equal to g by c. This condition is satisfied, then only attenuation constant is independent of frequency. Phase constant beta is linearly varies with the frequency. Square root of LC r by l is equal to g by c j omega. Here g by c j omega. That is equal to root LC g by c plus j omega whole square. That is equal to root LC g by c j omega. Root LC g by c j omega. But alpha is gamma is equal to alpha plus j beta. Therefore, alpha is equal to root LC g by c root L into root C g by root C into root C cancel. Therefore, g into square root of L by C. Square root of L by C. Beta is equal to omega root LC. Omega root LC. Here gamma is equal to root LC R by L R by L j omega. For distortionless line, G by C is equal to R by L plus j omega. Therefore, root LC is root LC R by L plus j omega. Alpha plus j beta. Alpha is equal to root LC into R by L. Root L into root C R by root L into root L. R into root of C by L. Therefore, beta is also beta is equal to omega root over LC. Alpha is independent of frequency. Beta is a dependent frequency. In all the cases, alpha is defined as root RG. Alpha is equal to root RG. That is equal to, here alpha is equal to G into root L by C. Next, one more expression is R into square root of C by L. Beta is equal to omega root LC and also omega L root G by R, omega L root G by R. And one more important point is omega C into root R by G. Omega C into root R by G. Next one, when the line is free from the frequency and delay distortion, it is said to be distortionless transmission line. When the line is free from the frequency and delay distortions, it is said to be distortionless transmission line. Distortionless transmission line. That is the line is distortionless when the attenuation constant is independent of frequency and the phase constant is linearly depend on the frequency. When the line is proved above with the help of the equations, the line is when the line is distortionless, the attenuation constant is independent of frequency. And the phase constant is linearly dependent on the frequency. The distortionless transmission line exists when the distributed parameters of the line are related as follows. That is, R by L is equal to G by C. The distortionless transmission line exists when the distributed parameters means R, L, G, C. Distributed parameters of the line are related as follows. R by L is equal to G by C. Next one, group velocity. Second one is phase velocity. Second one is phase velocity. U is equal to omega by beta. Omega. Beta is omega root over LC here from this expression. Omega over root LC. That is root LC. Phase velocity U is equal to 1 by root over LC. Sometimes it is also represented as VP. Phase velocity is not changed with frequency. Phase velocity is not changed with frequency. There is no frequency component here. Next, the characteristic impedance. The characteristic impedance Z0 is equal to square root of R plus j omega L by G plus j omega C. The common term is L. R by L is j omega and C j by C j omega. That is equal to root L by C. R by L is equal to G by C. R by if the line is distortionless one, the condition is R must be satisfied. R by L is equal to G by C. R by L j omega. Here G by C is R by L j omega. These two are cancelled. Therefore, characteristic impedance Z0 is equal to root over L by C. Root over L by C. Another Z0 is equal to R plus j omega L G plus j omega C. Here R is the common term. 1 plus j omega L by R. Here G is the common term. 1 plus j omega C by G. R by L is equal to condition distortionless transmission line. R by L is equal to G by C. R by L is equal to G by C. Or L by R is equal to C by G. That is equal to R by G. Z0 is equal to R by G. R is equal to root over L by C. Root over L by C. The phase velocity is independent of frequency. Phase velocity U or Vp is equal to 1 by root over Lc. The characteristic impedance of the waveform Z0 is equal to 1 over root Lc. Both are equal. The phase velocity is independent of frequency. There is no frequency term in that expression because the phase constant beta linearly depend on frequency, that is equal to beta is equal to omega root over Lc. The beta is linearly depend on frequency term omega. But group second point is phase velocity and Z0 remains same for distortionless transmission line. Distortionless transmission line. With this, the analysis is complete.